Solved problems. Let us look at the semantic proof of negation left parenthesis a and b right parenthesis implies left parenthesis negation a or negation b right parenthesis. This is an example of the so-called De Morgan law. We start with the negation of the formula to be proved. So in this case it is a negation, left parenthesis negation, left parenthesis a and b right parenthesis implies left parenthesis negation a or negation b right parenthesis twice. And first we use the implication rule. We get two formulas. First, the hypothesis of the implication, and then the negation of the conclusion of the implication. This is what it means for an implication to be false. Hypothesis is true, but conclusion is false. Now we use the disjunction rule. The negation of the disjunction means that both disjuncts have to be false. So we get the negation of both disjuncts. We get negation A, that's a negation of the first disjunct, and negation B, which is a negation of the second disjunct. Finally, we apply the conjunction rule to the negation of the conjunction of A and B. Now, the negation of the conjunction splits the tree. This is because for the conjunction to be false, it suffices that one of the conjuncts is false. So we split into the two cases, A is false and B is false, which we write as negation A on the left and negation B on the right. Now we have reached a tree in which both branches close. On the left we have negation A and negation A, and on the right we have negation B and negation B. So this tree is a closed tree. And this is the semantic proof that we were looking for. We give a semantic proof of left parenthesis A or B right parenthesis implies left parenthesis B or A right parenthesis. This is a kind of symmetry law of disjunction. We start with the negation of the formula to be proved. So in this case it is the formula negation left parenthesis A or B right parenthesis implies left parenthesis B or A right parenthesis twice. And we apply the implication rule to this. So implication is false means that the hypothesis is true and the conclusion is false. Next, we apply the disjunction rule. Disjunction is false means that both disjuncts are false. So we can write under the negated disjunction the negation of the first disjunct, that is negation B, and then the negation of the second disjunct, that is negation A. Finally, we use the disjunction rule. The disjunction A or B causes the tree to split, and it splits into A and B. Because disjunction of A and B means either A is true or B is true. Now we have a tree in which again both branches close. The leftmost branch has A and not A. The rightmost branch has B and not B. So this is a closed tree, and it constitutes a semantic proof of the formula that we wanted to prove. We give a semantic proof of left parenthesis A and B right parenthesis implies left parenthesis B and A right parenthesis. So this is a kind of symmetry law for conjunction. We start with the negation of the formula to be proved. So in this case it is negation, left parenthesis A and B right parenthesis implies left parenthesis B and A right parenthesis twice. First we use the implication rule. The negation of the implication means that hypothesis is true and conclusion is false. Then we apply the conjunction rule. Conjunction A and B allows us to write on this single branch that we have A and then B. Finally, the negation of the conjunction in the middle of the branch causes this branch to split, because conjunction is false if at least one of the conjuncts is false. So we try maybe B is false or maybe A is false. Again we have a tree in which both branches close. Leftmost branch has not B and B, and the rightmost branch has not A and A. So this is a closed tree, and we have obtained a semantic proof of the formula to be proved. Here we give a semantic proof of negation A implies B. We start by writing down the negation of the formula to be proved. So in this case, negation, left parenthesis, negation A implies, in parenthesis, A implies B, right parenthesis. First we use the implication rule. We have a negation of an implication, so we write underneath the hypothesis and the negation of the conclusion. Now we apply again the implication rule. The implication A implies B is marked as false. That means that we can write the hypothesis A underneath, and then under that the negation of the conclusion B. So we write negation B. We have a semantic tree which has only one branch, and on this branch we see both A and not A. So we have a closed tree, and this tree is a semantic proof of the formula that was given. Here we give a semantic proof of the formula left parenthesis P0 and left parenthesis P0 implies left parenthesis P1 or negation P0, right parenthesis implies P1. We start with the negation of this formula. So we have a formula which starts with negation, then comes left parenthesis twice P0, and left parenthesis P0 implies left parenthesis P1, or negation P0, right parenthesis 3 times, implies P1. This is the negation of an implication. So we use the implication rule, we write the hypothesis and the negation of the conclusion. Now, on the second row of this tree we have a conjunction, so we can write as an extension of this branch both conjuncts separately. So first we have P0, and then we have this implication. P0 implies left parenthesis P1 or negation P0 right parenthesis. This is an implication, not a negation of an implication. So looking at the rules of semantic trees, if we apply the implication rule, the tree splits here into not P0, the negation of the hypothesis, and the conclusion P1 or not P0. This is because the truth of implication means that either the hypothesis is false or the conclusion is true. This is why the tree splits here. On the right-hand side, we still have a disjunction, and although we can see that the leftmost branch is already closed, it has both not P0 and P0. The rightmost branch is not apparently closed yet, so we apply the disjunction rule and we split the tree here into P1 and not P0. Now we have reached a tree in which all branches close. The leftmost branch has not P0 and P0. The middle branch has P1 and not P1. And the rightmost branch has not P0 and P0. So this tree is a closed tree, and this tree is a semantic proof of the formula that was given.